Very good day to Dr. Rahim. My name is Ryan Gee with the metric number 201091046. I'm from Group 1. Today I would like to present my open-ended laboratory 3, which is talking about the DC machine. So we will be touching on to DC series motor, DC shunt motor, which is self-starting DC, and we're talking about the separated starting DC. So the difference between the DC series and the DC shunt will look into the characteristic. The objective is we are able to perform the experiment to characterize the DC machine, and so to analyze and observe the results, and then to understand the limitation parameters such as the magnetization of the curve, as well as looking how to control the speed. So this is a schematic diagram as well as the lab we carry out practically. And then this is for the DC shunt equivalent circuit schematic, and this is the one we carry out practically. These are the methodology, the steps that we've taken for the DC series. We're talking about the connection and motor direction, where we are learn to how do we get the clockwise rotation, acting clockwise rotation due to the left hand Fleming rule and the right hand Fleming rule. And then we're talking about the stop and speed characterization, the methodology. And then we move on to the speed control, where we are going to measure the resistor and the armature current. So this is the last one, the magnetization of the DC shunt motor, where are the procedures. So these are the connections. So basically, as I mentioned, the anti-clockwise direction is because the configuration are reversed. So we're using the Fleming's left-hand rule. So we want to make it to a clockwise, we will reverse the arrangement between the A1 and A2 connection, which is on top of the DC machine, the motor. So the speed torque characterization, the torque has been varies from 0.02 to 0.16. We can see that the speed is decreasing. So when we put into our plot, into our graph, torque versus speed, actually when your torque is increases, your motor speed decreases, which is inversely proportional. Alright, next one, we will talk about the armature current and the torque relationship. So when armature current and torque relationship of this DC motor is actually directly proportional, because due to the formula of T induced is equivalent to flux multiplied by your armature current. So as your flux decreases, your armature current increase as well, your torque increase. So we move on. Of course, we will talk about we will do derivation of the formula is actually IA squared, which is your current will be squared. Next, we'll talk about the speed control, your current resistance, and your field current and your armature current is actually inversely proportional as well. As your field resistance increases, your armature current decrease. Next, you'll move to the magnetization of the curve for the DC shunt motor. So we're talking about fixing your speed at 1770 your RPM. This for the magnetizing graph. And then this is the practical result, where basically when your field current increases, your open circuit terminal voltage also increase. This is due to because the calculation through here, when your RF decrease, your IF increase. When your field current increases, your flux increases. When your flux increases, and then your flux increases due to makes your open terminal voltage increase as well, because they are connected, they are interrelated. Next, we're going to compare the performance between shunt field winding and the series field winding. So actually, as the sound in the introduction, the series field winding or DC field motor is actually they are series. For DC shunt, they are parallel. We look into the characteristic. The torque is directly proportional to the square of the armature current, whereas the torque is directly proportional to the armature current for the DC shunt. And then we're going to talk about the torque. The starting torque developed by the series motor is high compared to the shunt motor, as well as the starting torque developed by the shunt motor is lower compared to the series. We move on the field application to be used. This is the efficiency rate. We can see that as the fuel resistance decreases, you can see your efficiency also decrease from the data. This is for your DC series motor. And then we move to the next one is the efficiency rate for the DC shunt. As your DC resistance decreases, your efficiency increase. So it's actually vice versa, because this one, when it decrease, your efficiency decrease as well. Or DC shunt, as your resistance decreases, your percent your efficiency increase. So you're gonna propose and illustrate DC separator. Why actually DC separator is more preferable over the self-exciter is because they are usually used when for testing purposes because they have give a wide range of voltage output from a very simple look. We can see that actually in comes to DC separator you can have two voltages. One's your field voltage, one's your terminal voltage. When it comes to DC self excited DC, and actually you have one terminal voltage. That's the basically the very big difference we can see. Of course, you can get better readings using the DC separator connector motor. What are the recommendation? We have few recommendation to obtain optimal efficiency. Number one, we will eliminate the voltage unbalancing. We will replace the V belt with clock on synchronous belt drive. We will avoid nuisance tripping as well, maintaining the motor shaft alignment. So that's it for my presentation for my OER3. Thank you very much and have a good day ahead. Thank you.